Okay, so we're going top to toe through the physiological systems that are affected by spaceflight. And so we're going to start with the neurological changes. So on the slide are diagrams of the vestibular system, which is part of the inner ear. So in the first few days upon entering microgravity, for up to about 72 hours, astronauts experience a type of motion sickness, which is generally referred to as space adaptation syndrome. This is due to a mismatch of signals involving the vestibular system. Otoliths are small particles inside the inner ear in the utricle and the saccule, which you can see in the diagram on the right-hand side. When we move our heads, these otoliths disrupt cilia or small hair cells inside the utricle and the saccule. And the displacement of these cilia means that we can detect change in movement in our heads. In microgravity, these otoliths start to move around, and therefore the cilia experience signals that they don't usually when we're on Earth. So this means that there's a mismatch between the visual cues that you're getting from your eyes, i.e. your head is staying still, and the signals caused by the movement of the cilia, which suggests that the head is moving. This mismatch can cause quite extreme nausea in astronauts, and they feel unwell during their first few days in space, particularly on their first mission. Astronauts report getting used to this feeling after a certain period of time, but a lot of astronauts are sent with anti-nausea medication, particularly on their first flight. So the next thing is a reduction in visual acuity. The main theory proposed for this reduction is an increase in intracranial pressure, or ICP. There's a fluid shift that happens in spaceflight. So fluids that are usually held down by gravity in the lower part of the body start to shift upwards. This is why you often see astronauts with puffy faces when they're in space. This upward shift of fluid increases the volume of fluid inside the skull. The fluid is referred to as cerebrospinal fluid, or CSF. The fluid that sits around the brain, and it provides nutrients, removes waste products, and also provides mechanical protection. And it's thought that the balance between the production and absorption of CSF is also disrupted in spaceflight, and that this all results in an increased volume inside the skull. Given that there's only a finite volume inside the skull because it's a reasonably rigid structure, an increase in volume of CSF actually results in greater pressure on the brain. A study done took MRI scans of astronauts pre and post-flight. And you can see the comparison images on the screen here. And the three arrows in the center section, can you see my cursor if I indicate these? So these three arrows show an elevation of the border of the lateral ventricle, which is an area of the brain which is generally filled with this CSF. And this space being increased post-flight shows that there's an increased CSF volume in flight. But what does this mean? So the increased pressure inside the skull, the increased intracranial pressure, is thought to translate to the back of the eye, causing a globe flattening, where the usual curve of the back of the eye becomes flatter, as you can see in the left-hand image here. The movement of the back of the eye causes a hyperopic shift where astronauts become far-sighted. And many astronauts experience vision changes such that they require reading glasses of different strengths while they're in space. And there's even a box of reading glasses on the ISS to mitigate this. You can also see the fundal photographs, or the photographs of the back of the eye, on the right-hand side of this slide. And you can see the arrow in the bottom left shows these kind of faint lines across the back of the eye, as indicated here. These are called choroidal folds, and it's a buckling of the choroid layer of the back of the eye. Another change that we often see in these photographs is called papilledema, which is a swelling of the optic disc. As you can see, the images at the top here are pre-flight and these are post-flight. And if you look at the optic disc, which is the lighter circle, the border of this disc becomes slightly fuzzier and less well-defined, which is indicative of the swelling. Now, all of these changes come under a syndrome which is known as SANS, Spaceflight Associated Neuroocular Syndrome. We don't yet have the full details of exactly what causes this condition or how it changes over time. We know that long duration spaceflight appears to have a greater prevalence of SANS than short duration spaceflight, with approximately 2/3 of astronauts experiencing visual changes after 6 months, compared to about 1/3 on short duration flights. However, we're not yet aware of whether it plateaus after time or whether it continues to get worse. And should it continue to get worse indefinitely, this could certainly have a serious impact on future missions to Mars and beyond. There's also an interesting point that it tends to affect the right eye more than the left. And we don't yet know whether that's completely statistically significant, but it would be interesting to see in future studies. So the next thing I'm going to move on to is the psychological impact of spaceflight. So there's a phenomenon of us versus them, where the crew form a small unit on the International Space Station and they're completely removed from the crew on the ground. They can therefore feel slightly disillusioned, or there might be interpersonal tension between the astronauts in space and the ground crew. There's also a phenomenon known as the overview effect, where astronauts have previously talked about a kind of perspective shift when they experience when they're in space. Looking down on the Earth from above, they become aware of the magnitude of the world and the absence of national borders, giving them a sense of almost unity of mankind. This feeling becomes increasingly profound during spacewalks because there's effectively nothing separating the astronaut from the vacuum of space. Another important psychological concept to think about is the effect of isolation. And this is likely to increase as we journey further and further from the surface of the Earth. It's a psychological phenomenon that's often studied in austere environments, but the idea of the isolation that you might feel on the surface of Mars when the Earth is just a tiny speck in the sky, it can't be overlooked. Another important factor is the idea of sleep hygiene. So on the ISS, astronauts orbit the Earth every day or sunset every 45 minutes. This disturbs the natural circadian rhythm of sleep and wake. And the International Space Station runs on Universal Standard Time, UTC, which is the same as Greenwich Mean Time. The schedules of their day are planned according to this, and they are given a specific time to sleep. And there was recently an introduction of blue LED lights on the International Space Station to try and give them a sense of natural daylight time and then dark for sleep time, to try and regulate the natural sleep cycles of astronauts. And in terms of interventions for their psychological well-being, astronauts have private video calls with their families and friends while they're on the ISS. And they also have weekly medical consults with their assigned flight surgeon, so that they can talk about any physical problems as well as psychological well-being. So the next, coming down top to toe, the next thing is the heart and the cardiovascular system. So there are several changes that happen to the heart and the vascular system in space. Over time, the average blood pressure of astronauts drops to a lower set point. And this is due to the fact that receptors in the blood vessels detect extra stretch due to the fluid shifts and respond by appropriately dropping the blood pressure. So if you look at the diagram on the slide, this is a person on Earth, and in terms of blood pressures, you think of a column of blood from top to toe. And then as you go into microgravity, there's the upward fluid shift. So blood that's usually held down in the feet is kind of free to move throughout the body. And then over time, that set point lowers so that the pressures are the same above the heart. And then that means that then when you come back down to Earth after flight, when that blood starts to pool in the lower extremities again, you have a lower blood pressure above the heart. Over time in space, extra fluid is also excreted by the kidneys, which means that you have a lower plasma fluid and a lower blood volume in space. This then causes a problem when you return to Earth, because, like I said, the blood then pools in the lower extremities again, and astronauts will then have issues with adequately perfusing their brains. So sometimes astronauts faint if they have to stand for long periods of time after flight, and this is due to that blood pooling and the blood being pulled away from the brain. So then the astronaut faints in order to kind of reperfuse the brain again. Another thing is due to the decreased blood volume and the decreased resistance in spaceflight, the heart tends to change shape. So the myocardium or heart muscle is the same as any other muscle in the body. If you don't use it, you lose it. This means that over time, the heart decreases in size and becomes slightly rounder in shape compared to on Earth. And after flight, it takes time to build that muscle back up again. The respiratory system is quite interesting. So the lungs are one of the few systems that doesn't have any lasting effects, or doesn't seem to have any lasting effects in spaceflight. In microgravity, the tissue of the lung becomes more uniform. So generally, the tissue in the lower parts of the lung are more dense because they're being held down by gravity. And this is known as the slinky effect. So if you hold a slinky up, the coils of the slinky are closer together at the bottom compared to the top. And this is a good analogy to think about lung tissue. So then in microgravity, the coils of the slinky are more evenly distributed. This means that there's a slight mismatch of where the air flows compared to where the blood flows. So the airflow will be more uniform throughout the lung, but clearly the blood flow can't completely match that. And the statistic on the slide about end tidal O2 is indicative of that. So there's end tidal O2 is the amount of oxygen at the end of the expired breath. And the fact that there's this higher oxygen content in that is indicative of the fact that not all of the oxygen that's breathed in is being taken up by the blood. And like I said, the tissue becomes more homogeneous or more even in spaceflight, but this is not persistent when you return to Earth. So when you return to Earth and you're reintroduced to the effects of gravity, the lung structure goes back to normal. So there's no persistent change and no degradation of function when you come back to Earth. The next thing I want to talk about is nutrition and the gastrointestinal system. So due to the fluid shifts that we've talked about before, astronauts' sinuses become quite congested, and that kind of behaves similarly to having a bad cold. This means that their astronauts are generally less sensitive to taste during spaceflight, and they talk about wanting spicy foods. So I've said Tabasco, but also kind of hot sauce or anything spicy. These hot and spicy foods stimulate a particular protein channel in the mouth, which is called TRPV1, and it gives the sensation of heat. So it's the same reason that when you eat particularly spicy foods, you get the sensation of actual heat. And it's thought that this kind of hot sensation when eating spicy foods in space almost replaces the sense of taste, given that that's blunted in spaceflight. Astronauts also report a shift in dietary preference towards carbohydrate-rich foods. And studies have shown that this is indicative of physiological stress. So this is one of the things that I've found the most interesting, is that this is something tangible that we can see that demonstrates the stress that the body's under in spaceflight. So the image on the slide here is from NASA's archives, and it's of the diet of a shuttle era astronaut. So a lot of the food is dried and then rehydrated to be eaten, and they have a menu that lasts about 7 days and then repeats on the International Space Station, with the exception of holidays. They have different diets for holidays. This also impacts the astronauts psychologically because there's a decreased range of food that's available. And one last thing that I want to say about the nutrition is that hydration is a really important part to consider in nutrition. So astronauts lose water more quickly in space due to liquid excretion by the kidneys. So they have to drink more water in order to stay adequately hydrated. And this needs to be factored in when you think about the salt content of their diet and other things. So following on from that, I'm going to talk a little bit about the kidneys now. Astronauts have an increased risk of kidney stones. So this is due to the increased breakdown of bone in space, which I'll come to in a few minutes. And there is excess calcium in the blood due to this breakdown. The calcium is taken from the bones and then is excreted at the kidneys. Now this excess calcium can form deposits, which then cause the kidney stones. And the risk of kidney stones is also drastically increased by dehydration. So I'm sure you're starting to put together a picture of how everything links together in terms of space physiology. The next thing is muscular changes. So I've mentioned the concept of use it or lose it when it comes to muscle. And skeletal muscle is highly sensitive to the level of work that it does, which is why athletes who train have huge muscles, and then also the fact that you lose muscle if you are bedbound or have an injury. We have what are called postural muscles. So these muscles which are at work when you're sitting or standing or work to keep you upright. However, in spaceflight, there's no need to hold the body in that position. And actually your neutral position in spaceflight is slightly different. So the shoulders come forward, the spine is slightly curved, and the hips and knees are flexed. Think more similar to a kind of fetal position. Because of this, the postural muscles that generally work to sit us upright start to degrade. Astronauts lose a huge amount of muscle during spaceflight, and the one way that we've found to try and prevent this is through exercise. On the left, you see the Advanced Resistive Exercise Device, or ARED. It works on a series of bungee cords which create resistance similar to lifting weights. And on the right, you can see British astronaut Tim Peake as he ran his virtual London Marathon while aboard the ISS. And I don't know whether it's clear on the slide, but you can see over his shoulders, he has a tether to hold him down, to stop him floating away while he's running on the treadmill. Astronauts are allotted up to 2.5 hours a day to exercise, including equipment setup and clear up afterwards. Even factoring in that time, they get about 2 hours per day of exercise. And that's a huge amount. And it mitigates some of the muscle loss, but not all. The muscle loss that they experience in space particularly affects muscles such as the quadriceps, the calves, and some of the trunk muscles, which are the postural muscles that I talked about earlier. Interestingly, the upper body muscles have been found to remain largely the same during spaceflight. And this is thought to be to do with the fact that in order to get around in the weightless environment, astronauts use their hands and their arms to propel themselves. And their loss of muscle is intrinsically linked with the next thing that I'm going to talk about, which is the loss of bone. So the loss of bone works on a similar mechanism to the loss of muscle, which is due to the concept of unloading. Bone is consistently being broken down and built back up again. And the amount of that buildup is based on the degree of loading. So the weight that your body exerts on the bone causes stress, and the response is to build up the trabeculae. So you can see this crisscross section at the top of the bone, which is indicated by this arrow, compared to the section of long bone. So when that loading due to gravity is removed, the bone is still being broken down, but it's not being built back up as much. This leads to a state known as osteopenia, where you get reduced bone density. And this means that astronauts are actually at increased risk of bone fractures when they come back to Earth. Again, this primarily affects the long bones in the thighs and the lower body more so than the upper body. And also another interesting note here is that female astronauts don't lose so much bone density compared to male astronauts. And this is thought to be to do with levels of the hormone estrogen, which are protective to bone loss. So that's a kind of overview of the top to toe of space physiology. And then the next thing to talk about is things that affect the whole body. So the immune system doesn't function optimally in microgravity. You have a blunted immune response, which means that you can't fight pathogens so well. And this, along with the fact that bacteria and viruses have been found to be more potent in space, means that there's a real risk of astronauts becoming sick. To counteract this, astronauts flying to the ISS quarantine for a period of time before going, which I'm sure is something that we've all become increasingly familiar with recently. And this means that they don't take any bacteria or viruses with them that could cause harm to the other astronauts. Another big issue in space medicine is radiation. If I'm being honest, this could be an entire talk in and of itself. So I'm just going to give a kind of brief overview, and then I can direct you to some more research about this. So radiation causes damage to DNA and to cells, and it actually increases an astronaut's lifetime risk of cancer. And women have an increased risk with radiation exposure compared to men, because they have a greater volume of tissue which is susceptible to radiation damage, specifically the tissue in the ovaries, the breast, and the thyroid. On Earth, we're protected from a large portion of cosmic radiation due to our atmosphere, but on a journey to Mars and beyond, we need to provide adequate shielding in order to prevent some of the radiation damage that occurs. Astronauts in space also have a slightly higher core temperature, so TC is the core body temperature. Here you can see Alexander Gerst modeling a great look, which is a temperature probe on his forehead, and then he's wearing another one around his chest. And this was a study to look at the fluctuation in body temperature during day-night cycles. And they actually found that the core body temperature of astronauts was increased during spaceflight. This is thought to be to do with the fact that there's no convection in space, which means that heat can't be removed from the body as effectively. So sweat doesn't evaporate to remove heat from the body, and astronauts are not able to cool themselves as efficiently. This particular study found that a certain astronaut during exercise had a core body temperature of over 40 degrees, which is then bordering on hyperthermia, so astronauts getting too hot. And this is something that needs to be investigated further as we look to send astronauts on exploration class missions. There are also issues with drugs in space. So drugs can be less stable, and therefore they aren't effective for as long. But also the way the body absorbs and responds to these drugs can be altered. Space pharmacology is an entire field, and there's lots of absolutely fascinating research going on. And if anyone's interested, I'm happy to direct you to people who are experts in the field so that they can tell you more. But all of this information about the body in space doesn't come without its caveats. So all space medicine studies by definition have small sample sizes. Fewer than, I think, 600 people have ever been to space, and there's often only 6 people on the ISS at any one time. This means that studies are limited in their statistical power, and if any one participant responds in an anomalous way, or they get a result that they're not expecting, this can really skew results. It also means that studies have to go on for quite a long period of time to get a sufficient sample size in order to really see trends in the data. There's also the issue of ethical implications. So the truth is that, you know, if you're investigating countermeasures to try and mitigate against some of that bone and muscle loss in space, it's unethical to have a control group to compare to, because you can't, in all conscience, send an astronaut without those countermeasures, because the loss of bone and muscle would be too great. So for a lot of these studies, we don't have a sufficient control group to compare to. And I've talked about the fact that there are studies going on for quite some period of time, and general stay on the ISS for an astronaut only lasts about 6 months, and therefore we don't really have any data on the true long-term effects of spaceflight on the body. I think the longest single stay in space was just over 400 days by a Russian cosmonaut. And so as we look to establish permanent habitations in space on the moon or on Mars, we don't truly have an understanding of that long-term effect. And if we think that we have small sample sizes generally, we have even smaller sample sizes for anyone who isn't a reasonably athletic Caucasian male in space. Roughly 11% of all astronauts who have ever been to space have been female. And if you start considering the intersection of different demographics, it becomes painfully obvious that we need more representation to truly understand the effects of spaceflight on the body. So I've talked a lot about the physiological effects of spaceflight, but is that really space medicine? Well, space medicine and space physiology overlap pretty heavily, as I'm trying to demonstrate with this diagram. Given that all professional astronauts are rigorously screened for health conditions, space medicine up to now has pretty much been managing the physiological adaptations to spaceflight. However, as we look to the future, exploration class missions to the moon or Mars and beyond will require careful medical planning and resource management, as well as medical imaging and diagnostics and medical training, as well as genuine management of pathophysiology, so people with health conditions, rather than simply the adaptive physiology that we've seen so far. So one of the biggest factors in medical planning is launch costs. One estimate that I've read estimates that to launch a single kilogram of materials to Mars will cost over $1 million. That means that we can't rely on medical equipment such as bags of saline or medication which might destabilize or perish due to the spaceflight conditions. In this way, space medicine can learn a lot from wilderness and expedition medicine, which works on the concept of do what you can with the tools that you have. Inhabitants of future Martian or lunar cities will likely use 3D printing and local resources to produce medical equipment needed to sustain future treatments and interventions. And we need to look at the in situ synthesis of drugs, and this might be a future solution to some of the issues presented to drug stability now. Also, on longer missions, the likelihood of medical events increases. Physicians involved in space medicine now tend to be strong generalists. They have a very broad-ranging skill set, and some have specialist interests on top of that. However, imagine a Martian city with no specialist medical support. It's clear that in order to live permanently on another celestial body, specialist care is going to be needed. This is where the concept of just-in-time training comes in. Instructions on how to deal with specific medical scenarios can be recorded and can be accessed by clinicians should a highly specific event arise. This means that a physician doesn't need to be trained for every single eventuality that might occur during a mission, but can access the information if needs be. On the ISS, this isn't so much of an issue due to real-time communication between the ground and the space station, but with Martian communication delay looking to be about 20 minutes each way, self-sufficiency is going to be really, really important, and this is something that needs to be developed. So that's about all I have to say for now. I hope I've kept roughly to time, but I sometimes lose track because there's so much to talk about. I just wanted to say a quick thank you to all of the people on this slide for their support and their contributions. And if anyone is interested, you should definitely follow them all with their Twitter handles that I've listed. There is a link here, which I'm also hoping that Nina is going to post in the chat. And that's a link to a Google document, which contains the group links to groups that I've mentioned, websites for more information, and also some papers on the topics that I've talked about. I'm also happy to be contacted if anyone has any questions after this evening. And also don't worry if you don't grab my contact details now. If you contact a member of the Aberdeen Society Committee, they can pass my details on for you. And the last thing is I'm just going to briefly mention an opportunity. So if you have had some experience or exposure in aerospace medicine already and want an opportunity to present, the Next Generation Aerospace Medicine group that I mentioned earlier have released their call for abstracts today for their presentation competition. The competition is happening in December at the Royal Aeronautical Society's Aerospace Medicine Symposium. And this year our theme is celebrating women in aerospace medicine. We would love to have plenty of abstract submissions. So if you follow them on Twitter at NextGenASM for NextGen Aviation and Space Medicine for updates, you can find out how to apply there. And with that, I'm going to thank you all very much for your attention, and I'll open it up for questions.
Amazing. Thank you so much, Lauren. That was absolutely brilliant. I was hooked on every word. Even though I've, covered a little bit of this before in other courses, yeah, it's really nice to go over it again. And I think you give a really nice overview of all the many, many, many ways that space can affect the body. But yeah, and thank you for pointing out about the presentation competition, abstract competition, next gen aerospace medicine. That looks really cool. So hopefully some people in the audience will consider applying for that, perhaps. But yeah, I'm quite happy to open up the floor to questions. If anybody has any questions they would like to ask Lauren while we have her captivated attention.
Okay, so the link, Nina has posted the link in the chat as well. So there is a link there to like different papers and everything if people are interested. So
everyone's stunned into silence, I think.
Absolutely fine. If anyone thinks of a question after as well, I'm happy to answer them if they send me a message on Twitter or email or anything like that. So
I think this is just the evidence of how good your talk was and how you covered everything.
I launched 2 experiments in March, and they had very, very different themes. So the first one was looking at a type of flatworm called a planarian flatworm. And they've been found to have different regenerative properties in spaceflight. So these are tiny little worms. They're like 3, 4, 5 millimeters long. And if you cut their heads and tails off, a head and a tail will regrow. So effectively you get 3 worms if you cut the top and bottom. And there is a kind of mutation where if you cut the head and tail off, a head grows out of either end. So you have a 2-headed phenotype. And that mutation is found to be in about 1 in a billion on Earth, maybe. And it was found to be 1 in 15 in spaceflight. So we were studying the reason for that, looking at a specific cellular pathway. So we basically cut the heads and tails off a bunch of tiny little flatworms and then gave them certain medications to up and down regulate certain aspects of this pathway. And then the second experiment was looking at plastic degradation by a waxworm, so the larvae of a wax moth, which lives in beehives. And we were looking at whether the waxworm was able to break down polythene plastic in microgravity. I think there's a couple of questions from the chat.
Yes, we have a question here from Nikita. She asks, what book do you recommend on space medicine?
Oh, there are quite a few. There are some textbooks. Now, I will say that purchasing textbooks is crazy expensive, so absolutely don't do it. If you have access to a university library, they might have e-copies that you can kind of loan or try and get a hard copy out. So there's the Handbook of Aviation and Space Medicine, which is very useful. There's a textbook, I think it's J.C. Buckey, which is space physiology. You'd have to look that up, but there is a specific textbook on space physiology. I will find the details and pass them on to you, Adele, if you wouldn't mind distributing. So there are quite a few, but definitely the Buckey one is one to look at in terms of straight space physiology. The Handbook of Aviation and Space Medicine. I've got quite a few in my room, which I can go and like find and send photos of. But then also online resources are absolutely your friend. So the NASA Human Research Roadmap looks at various space medicine issues and how they're being addressed through research. Based on, I think they stratify them based on the risk that they pose to long-term missions. So yeah, there are plenty of resources out there. I've tried to link to some in that document that Nina's posted. So, and I'll send a list of recommended reading to you so you can distribute.
Excellent. Yeah, we might start a bit of a Twitter thread because I'm sure a lot of other people would have some good recommendations to add to that as well.
Definitely.
There's a question here from Wei Pen. who asks, how can we get involved in the space physiology / medicine / astrobiology experiment? I'll let you answer that, Lauren, but I also want to mention that same time next week, we will have a second member of the Paraboladies, Nina Purvis, and she will be doing a talk specifically on how to get into space medicine as a medical student. So some part of your question might be answered there, but of course, I'll let you add to that as well if you like.
Well, I was going to plug Nina's talk as well. Nina is a fantastic speaker. She's going to hate me for shouting her out like this, but she's a fantastic speaker, and she talks a lot about how you kind of go and get these opportunities that are available to medical students, and even like life sciences students. Everyone can get involved in space medicine. So yes, that's one of the things. There are several people throughout the UK who are more than willing to talk to people about how to get involved. So, I mean, I've had a couple of people message me recently on Twitter going, I find all of this stuff really cool, but I don't know where to start. Where can I get involved? So, and all of us, I can't speak on behalf of everyone, but everyone that I know certainly is more than happy to answer those questions and talk to you about the experiences that they've had and how you can get involved as well. And in terms of like specific student groups, so the next generation group that I've mentioned is specifically aimed at students. Then there's also other groups. UK Space Labs are another good institution to look into. And the Aerospace Medical Association has a student branch called AMSRO, which is AMSRO, so the Aerospace Medicine Student and Residents Organisation. They also have really good resources and opportunities to get involved as a student as well.
Brilliant, thank you very much. We have a similar question from Nurul, I hope I'm pronouncing that correctly, who asks if it's possible to be involved as an international medical student. And similarly, I would say come along to Nina's talk at 7 o'clock next Thursday, same time next week. I think her talk is mostly focused on UK medical students, but there are bits and pieces that she will mention that definitely account for international students and pretty much anybody. I would say, as a starting point, perhaps depending where you're from, look at the space organization, if there is one, kind of connected to your country. So for example, if you're in the US, have a look at NASA. If you're somewhere in Europe, have a look at ESA, etc. And certainly that can lead you down a rabbit hole of quite a lot of different bits and pieces, resources, opportunities and contacts, etc.
Another thing is the International Space School Education Trust that I mentioned earlier. I promise I'm not just shouting them out because I got to send experiments to space with them. Like, it's not sponsored at all. They run the summer program that I talked about that I've mentored on. They run it in several different countries. So they had iterations in Australia and Singapore and India. I think they're trying to get something set up now in terms of the US and Canadian side of things as well, maybe. I don't know, don't quote me on it. But that's an international endeavor. So another good thing that's kind of developed recently is the fact that, you know, clearly due to all of the situations this year, a lot of people are working remotely. So there's more opportunities in terms of international remote working. So if you find someone who does, you know, cool research and you're interested in getting involved, send them an email and see if it's possible to get involved remotely as well.
And certainly with a lot of things, not just space medicine, a big piece of advice that I give a lot to give to a lot of people is, you don't ask, you don't get, kind of thing. The worst that can happen is you reach out to somebody and they either say no or you just don't get a reply. There have been some pretty amazing experiences I've had just by leaping out and taking a chance and just emailing someone and hoping for the best. So yeah, I definitely recommend giving that a go. Will, do you have sorry, did you want to say something else?
Yeah, so I was just going to say, like, my relationship with my mentor started by me being 17 or 18 and sending her a tweet being like, I want to find out more about space. And she like sent me a DM, and then I've managed to kind of develop this professional network through Twitter and sending people emails and just being like, I find what you do really cool. Can I learn more about it? So no one is ever going to say know if you tell them that what they do is fantastically interesting. So that's
It does respond very well to flattery. I can confirm. Yeah, no, absolutely. And not just reaching out by email, like you mentioned, Twitter is an incredible networking tool. Just follow absolutely anybody and everybody that's got space somewhere in their bio or mention space at all. Yeah, and I think, to be honest, I think that's how we have ended up with 42 participants in this call at one point. But yeah, no, it's a good move to make. I'm losing track of everyone's names.
Could I ask another question? This is less about specifically space med, but you talked about doing out in terms of like nowadays where there's not a lot of in-person uni, you can't really go out and do outreach at schools or whatever level you're doing it at. How do you think the best way to get involved with that?
So in the UK, there's STEM ambassadors. So STEM ambassadors are like a great kind of central hub for people wanting to do STEM outreach. And they are doing remote sessions. So you can link up with schools who need people to do talks and things like that. You can do that all remotely. But also, again, it's just a fact of like getting in contact with people and saying, I want to kind of do some outreach. Is there any like schools that want to like Skype? So there's a kind of initiative called Skype a Scientist as well. That's another thing that you can do remotely. Granted, it is more difficult at the moment because people aren't meeting in person. So there's kind of fewer opportunities, but there's definitely ways to do that remotely. If you send me a message, I'm happy to kind of put you in touch with like relevant organizations and stuff.
Yeah, thanks. That's a lot of help.
Cool.
Yeah, I hear what you say about coronavirus messing everything up. And, I don't think there's a single person on the planet that would disagree with that. Yeah. But I think, you have to look at the silver lining. And I think in a lot of ways it's made some things easier. So as more things become more and more online, it makes things a lot more accessible for people. So where, a certain speaker might only do things in person in a specific location, when that now comes online, that's opened up to the rest of the world, so long as you're awake in their time zone. So it's bringing a lot more people together and opening up kind of information and resources in a way that wasn't as doable before, perhaps. So we have a question from DR here. Is aerospace medicine recognized by the GMC yet as a subspecialty? Lauren.
Yes, aviation and space medicine is a recognized GMC specialty. It was recognized in 2016, so there is an official training pathway. So it used to be a subspecialty of occupational medicine, but it now has its own recognition. So the Faculty of Occupational Medicine website has a list of the learning objectives for the specialty and the kind of core competencies that you need. So most people go into the specialist training from an acute care background, anesthetics background, GP or emergency medicine. So they're the kind of four most common things that people start in and then move across to aviation and space medicine. Yeah, it's an officially recognised training pathway. And some of the people involved in the Royal Aeronautical Society and everything are on that pathway. So they'd be kind of better placed to be able to answer your questions about the training pathway specifically.
Okay. Do we have any more questions? I think that might be us.
Perfect.
Either that or everybody's just absolutely stunned into silence. But either way, I'd just like to take a moment to say thank you so much, Lauren, for taking the time to speak to us tonight. I thought that was absolutely brilliant. For our participants here, I'm just going to drop a link in the chat to a feedback form. We'd be really, really grateful if you could fill that out for us. And there's also a section on the form for you to add your name and your email address to receive a certificate of participation, which is sometimes nice for the old portfolio to give you evidence of having done extra things out with your studies, which is always great. And aside from that, we'd be really grateful, and I'm sure Lauren would be really grateful for any feedback, good or bad. We're tough skin, we can take it if you've got anything you'd like to add. And there's also a section on there if you'd like to be added to our mailing list to hear more about the Society's events, then fire your email in there and we can get you kept in the loop. But otherwise, brilliant.
Thanks very much.
Thank you.